Good evening again, and thanks for being here. My name is Francesco Topputo. Some of you already know me. I'm an associate professor with the Department of Aerospace Science and Technology, upstairs, this building. And I'm with Polimi since a few years now. This evening's topic will be about LUMIO, and the title of this talk is LUMIO Mission Thinking Inside the Box. So, which means a couple of things already. LUMIO is a mission, and we will see later on what's the acronym for, and it's a mission. It's a space mission to the moon. Otherwise, it won't be within this event. Thinking inside the box is actually something that means that LUMIO is a box itself. So usually we have been used to think outside of the box. But in this case, we'll see how to think inside the box is useful for miniaturized space missions. And I already revealed that LUMIO is a small piece of spacecraft. All right, so our time together will be around 30 or 40 minutes, depending on how much interested are you later on for what concerns the questions. And I will try to squeeze a lot of work that we did into these few minutes, especially for what concerns the mission and why this mission. So why we want to do this kind of science, and then I will take some time to give you an overview of the most important ingredients beside the mission, which means the instrument, the scientific instrument of the mission, the selection of the orbit and the astrodynamics itself, and the system, together with some conclusion. But before that, I'd like to make a step back and to tell you all the story that originated all of this. So the European Space Agency issued a call at the end of 2016, and the call was called LUCE, Lunar CubeSat for Exploration. So they asked all of the European community to give them ideas for CubeSats. I guess many of you, almost all of you, know what a CubeSat is. It's a small miniaturized satellite or spacecraft, depending on where it goes, which is the size of a shoebox, more or less. It's made of units, and each of the units is a cube, which is 10 centimeters side and 1.3 kilogram mass. This is the standard. Anyhow, ESA issued this call at the end of 2016, asking for ideas from the community. So we need to have a few weeks to give a few pages. I guess it was 15 pages on a possible ideas. And they evaluated these ideas. So I've been told that there were about 40 consortia that delivered their ideas by the closure by the deadline, which was December 2016. Then they evaluated this idea. They made a short list. And LUMIO was actually shortlisted. So they made a short list. They went from 40 ideas to 4 ideas. They shortlisted 4 consortia, and these consortia were contracted. They paid us, actually, to make this idea more mature, to refine the idea. We kicked off in mid of 2017, and we had 6 months to deliver a preliminary, this is called phase 0 report, with our finding in this phase that was called challenge analysis. There was a second evaluation, and then there was a final review at ESA in the Netherlands. in which the 4 teams, it was 1-day review for each of the teams. So it was a 4-day review together with the final public review, because the other reviews were restricted between the team and the ESA, and then the winners were announced. Now it came out that LUMIO was the winner of all of the competition, ex aequo with another team called the VMMO, which is another mission for detecting volatiles on the lunar surface. And by winning the competition, we underwent a CDF study. CDF here means Concurrent Design Facility, which is a facility at ESA where they can, in few sessions, they can perform a preliminary design of a space mission. So what we did here was to have an independent review of our project done by the ESA expert. The review concluded that the mission is feasible, and now we are in talks with European Space Agency, Italian Space Agency, and Dutch Space Office to put together a budget to go to next phases of the mission. And I've been told that we will kick off next phases of activity in few weeks, if not few days. Anyhow, this was the whole story in a nutshell. It was, as I said, a huge amount of work. And LUMIO was awarded winner of the competition. What's LUMIO for? LUMIO stands for Lunar Meteoroid Impact Observer, and is a 12-unit CubeSat that will observe and quantify the meteoroid impacts on the lunar far side from Earth-Moon L2, which is the second Lagrange point of Earth-Moon L2. As I said, it was awarded winner of the competition, and it was assessed independently by ESA. Let's see the mission in a little bit in more details. In the statement of work was required that a CubeSat was already injected into lunar orbit by a mothership. This was given. How to go to lunar orbit was not the matter of the study, because there will be a lunar orbiter here carrying along small CubeSats as payload, and this CubeSat will be delivered in lunar orbit. So the transfer to the moon was not part of the study that we did. So the assumptions are that the CubeSat is injected into lunar orbit. It undertakes a transfer from low lunar orbit to Earth-Moon L2, and it acquires an orbit around L2 here, a quasi-halo orbit around L2, from which it can permanently observe the lunar far side. After 1 year of lifetime, the CubeSat is disposed, and the mission concludes. Okay? This is the mission profile. There are a number of challenges and interesting features of doing this kind of mission. First of all, we will see why this kind of scientific investigation is important, and if you agree, I will push this in 5 minutes' time, because we need a little bit of time to understand why this investigation is important. It's quite a big technological challenge, because there haven't been lunar CubeSats so far. CubeSats have been a nice academic first and industrial standard, because nowadays they are the standard for what concerns low Earth orbit. But when you pick the CubeSat and you move it in the deep space, it's a huge technological challenge in terms of power production, communication, thermal protection, radiation, fine pointing, because you don't have any magnetic field in the deep space, and orbital maneuvers, okay? Because standard CubeSats don't have any kind of propulsion. So you have to enable a number of technological currently existing gaps. So there haven't been lunar CubeSats so far, and we had a number of other issues. For instance, the sophisticated orbit. We have autonomous navigation here, because the idea is that the cost of the mission scales with the mass of the system, but operations don't scale if you treat the CubeSat as a standard satellite. You have to change also the paradigm on how you operate it, okay? So you have to enable some sort of new ways of, for instance, self-determining the position of the CubeSat. For what concerns exploration, it's flying a CubeSat into lunar environment. It's a record itself. We want to boost lunar situational awareness, because whenever you foresee to plan, whenever you foresee to establish either robotic or human outposts on the lunar surface, you need to know what's happening there, and you need to know whether or not, for instance, a meteoroid shower is happening or not, and so on and so forth. This video shows, in a nutshell, the mission profiles, just for you to understand, and then we will see why this scientific investigation is important. So the transfer is not relevant, as I said, but this is just an artist's impression. It was made by our friends from EPFL. Here we have LUMIO, which is this box, and this is the lunar orbiter. They go on a transfer to the moon. I'm afraid this is the moon. And there are a number of orbits around the moon, and at some point LUMIO is injected here in lunar orbit and goes in an orbit around Sun Earth L2. This is to scale. This is not off scale. So, and you can see that always the Earth and the moon are always visible from this orbit. While on Sun Earth L2, LUMIO points the dark side of the far side of the moon and spots for these spikes in the visible spectrum to detect whenever a meteoroid impacted the moon. And this is done to improve our knowledge of the currently existing models of lunar meteoroids. We will see this in a sec. Now, this was a mission in which Polimi was the prime contractor and was the coordinator of the study. I was the PI. I was the principal investigator of the study, and the team was made of Polimi, TU Delft, and EPFL as European university. Then we had two companies, S&T from Norway. S&T is a Dutch company, but the Norway branch worked on it. And Leonardo, which was former Finmeccanica, for those of you that still know it with that name. And with another American university, which is University of Arizona. All of it was, as I said, supervised by ESA. There were a number of people involved, and I've already seen at least 4 or 5 people that continued working on LUMIO. I'm afraid this chart reports the people that worked for the phase 0, so the people that worked for the study that was awarded winner, but I've seen at least 3 or 4 faces in the room that worked on the mission, and I apologize for not acknowledging them in this chart. As I said, this chart is from 2017. By the way, so there were a number of people from Polimi, from TU Delft, from EPFL, S&T Norway, Leonardo, and the University of Arizona. All right, having said that, this was more or less the forward of all of it. Let's see a little bit more in details why we want to do this, why the idea was interesting, why we won the competition. All right, so why studying near-Earth objects? Near-Earth objects are the result of, as you know, planet processing in the solar system and formation. And therefore, they have not been subject to the same processing as planets or moon, so they still embed some piece of information that has been kind of frozen since a million years there. And therefore, they embed relevant informations in it, and they are a nice source to investigate. That's why nowadays you have a lot of missions that are going to the minor bodies. You have the Japanese Hayabusa, NASA's OSIRIS-REx. There will be ESA's Hera mission, for instance. There are many missions that want to go to study the minor bodies because they have a lot of information in them, and they are a piece of objects that is worth to investigate. By the way, it's much cheaper to have a mission to an asteroid than having a mission to a planet, but this is another different story. That's another reason for all of the people going to study minor bodies. Anyway, meteoroids are the products of the processing of the near-Earth objects. So whenever a meteoroid becomes visible, it's a piece of near-Earth object that can be studied itself. So meteoroids are a nice, studying meteoroids is a nice opportunity to study the parent object that originated the meteoroid. So they are as well valuable resources to study. Let's see this phenomenon on meteoroids. Now, meteoroid is a piece of rock traveling in the solar system, right? When a meteoroid enters the atmosphere, it becomes what? A? No, a falling star, it's okay, but that's for kids. It becomes a meteor, and when it reaches the ground, it's a meteorite, okay? So meteoroid, meteor, meteorite, okay? So meteoroids are rocks, like 1 kilogram, 10 kilogram size, that move in the solar system. Now, what happens whenever they move? We will see later on in formation. And what happens, for instance, suppose this is the sun and this is an orbit around the sun. What happens whenever this meteoroid intercepts a planet or a moon? Well, whenever this happens, you have the so-called meteor showers. Do you know by chance a meteor shower happening in some precise date of the year? That's it. That is the 12th of August. Okay, not the San Lorenzo, for instance. It's an exact date in which this group of rocks intercept the Earth there every year, always at the same location. There will be a nice video in a sec. What happens when there is an interception between the meteoroids and the planet or the moon? We have, as I said, the meteor shower. Now, this phenomenon is a very high-speed phenomenon because the maximum theoretical velocity at which the encounter happens is about 70 kilometers per second. Now, this is easy to compute, okay? If you take an orbit which is in parabolic energy with respect to the solar system, and you compute the velocity at 1 AU, which is the Earth, and then you sum up, because they are in opposite direction, with the 30 kilometers per second, more or less, of the velocity of the Earth, you have easily 70 kilometers per second, okay? This is the maximum velocity. The minimum velocity is 11 kilometers per second, which is the escape velocity from the Earth. Okay? Now, one can think that this is the theoretical limit, but actually, there have been impacts that have been observed which actually approximate this velocity, because the orbit of the meteoroid is high elliptic orbit. Think of, for instance, at the orbit of the comets, which are high elliptic orbits, okay? They are just epsilon far from being a parabola, right? So if the meteoroid originated from the fragmentation of a comet, which is the case in some cases, then this velocity is high. So the kinetic energy is high. Just remember this. Now, just to make a little bit of a step back, why we have to study the meteoroids? Because we want to have models for the meteoroids in the solar system. You can say, why don't we point a telescope in the sky, in the night sky, and we have models? Because we are doing this survey. Yes, that's true. But we do the surveys to discover NEOs the size of this room, more or less. Lower than 20 meters, 15 meters, an object is very hard to be observed. So if we're talking about rocks which are this size, you can point whatever telescope you want in the sky, you'll never find it. You'll never observe it, right? So we want to have models for these things that cannot be observed from ground, unless something happens, which we will see in a second. Why we have to do this? Because we have to increase our confidence. If we want to send humans on the moon, we want to know what's happening actually out there, because as we will see, we expose them to a quite relevant risk. We want to characterize the population, and then we can contribute to other fields. For instance, hypervelocity impact physics, in which there is a mechanism called the partition of energy, which is not clear at all, which we'll see in a second. So we want to do this kind of observation. And beside that, we want to initiate a program that we took the liberty to call Lunar Situational Awareness. Now, let's see how the mechanism works. In this animation, credits are on this website, and I have to say that credits are also to my former master student, Gianmario Meriso, and current PhD student, which is sitting here in the back, because I grabbed this animation from his presentation. This shows exactly how the mechanism happens. Okay, this is still the orbit of the planets are the orbit of the planets, but this is a reconstruction of some sort of model. These are not real observations. So suppose there is this filament here. It's called filament, right? It's more dispersed toward the aposelane here, but it's less dispersed across the periselene. Okay. So this filament crosses the orbit of the planet. And as I said, whenever there is an impact, it's high velocity impact, so 70 kilometers per second. So suppose you have a rock 1 kilogram and compute its kinetic energy, 1/2 mv squared. We will see that the kinetic energy of 1 kilogram rock can release the same energy of a small nuclear bomb, more or less. Okay? What happens when this rock encounters the Earth? When this rock encounters the Earth, we have a nice protective blanket, which is the atmosphere, which, by the way, protects us by UV rays and also by these kind of things. Otherwise, we will be avoiding meteoroids all of the time. All of the kinetic energy is wasted in crossing the atmosphere when the rock reaches the soil. If so, it's already tiny, and it has given away all of its kinetic energy. However, the moon doesn't have any atmosphere, so all of the kinetic energy is directly released on the soil. And whenever a meteoroid impacts with the lunar surface, you have that the energy is partitioned into an excavation of a crater, because there will be a crater afterwards. And to produce that crater, you need some energy. There is a production of a seismic wave inside the moon. Some of the kinetic energy is given away in form of particles that are ejected from the impact site. And there is a small fraction of kinetic energy in the order of 10 to the minus 4. So we're talking about 1 every 10,000 parts of the kinetic energy that is transformed into thermal energy. The temperature of the particles can reach easily 2500 Kelvin, if not 3000 Kelvin. And this is a tiny part of the energy, so 10 to the minus 4. But since the kinetic energy is huge, 10 to the minus 4 of a huge number is a nice number. And you have that. A flash is emitted. So you have the emission of a radiation in the visible spectrum. It's like you light on a bulb for a fraction of a second. If you see this GIF here, I'm afraid it's visible. This is animation, right? This is real. This is a real GIF. You can see that this is the exposure time, and there are a number of frames taken. At some point, you have a spike here. You have a white dot appearing. It's a real impact that has been observed on the moon from ground. Okay, so suppose that we want to detect impacts with the lunar surface. We want to use the moon as a huge detector, okay? Because whenever an impact occurs, we can see the meteoroid. Otherwise, we can't. So we need a detector, okay? And we use the moon surface as a huge detector. You can even take a 10 by 10 meter squared stuff and fly it in the space until you get pierced, right? This is doable, but it will be a tiny surface. We have a huge surface of 1,700 kilometer radius out there that can be already a nice detector. We just need to point the telescope and use it to detect meteoroid impacts. Now, how would you do to detect this? There are programs that are currently running, one in the United States at NASA Marshall, and one in Europe, in Greece. It's called Meliota. And another one, there was another one in Spain, which I'm not completely sure if it's still running or not. How do these work? They have telescopes on ground. They point the telescope to the moon, and they try to detect spikes, luminous spikes, in the visible spectrum. Okay? The duration of the event is less than 100 milliseconds. Okay? In this case, you have 33 milliseconds exposure time for each frame. All right? Now, on ground, how does it work? Think of the geometry, right? So you have the Earth here, and you have your telescope. You can observe this kind of phenomenon only when the moon is by the green dashed arc, because you cannot observe the phenomenon when you have full moon. Why? Because in order to observe a local luminous spike, you need to have a nice signal-to-noise ratio, right? Which is the ratio between the phenomenon that you are measuring and the background noise. Okay? If the full moon, if you have the full moon, the background noise is so huge that you will never see a luminous spike out of it. So forget about this. The observations are done when the near side, I'm never talking about far side, dark side and of the moon, because there is no dark side of the moon as you can see here, right? There is near side and far side. There is no dark side. Okay, so forget about pink Floyds and so on. You can observe this from 50% illumination as seen from the Earth, and here you have zero illumination, here you have the new moon, and to 50% illumination. Across the new moon, you cannot observe it. Why can't you observe it? Why can't you observe meteoroid impacts when you have the new moon? Any idea? The answer is here. Because you have new moon when it's daylight, right? When it's our day, and once again, signal to noise ratio will be correct. Okay, so you do that only in this portion, and there are a number of limitations. Because and why the line is dashed? The line is dashed because you are on the Earth, and the Earth is rotating around its axis. So you cannot have any continuous observation. You have few hours per night, plus you are also constrained by weather. If it's cloudy, forget about it. Okay? So there are a lot of limitations. We can go in the space because we can have some uninterrupted observation. We can observe also other sources that nowadays cannot be detected. For instance, these sources, anti-helion, those that come from the opposite side of the sun, cannot be observed. Okay, and you can complement ground-based observation. If you go to L2, and you will be in the blue circle. If you go to L2, you can have continuous observation, and you don't have the so-called earth shine. What's the earth shine? Whenever you observe a meteoroid from ground, signal to noise ratio, so the background is this portion here, which is not illuminated, but however, you have some illumination given by the sunlight bouncing on the Earth and hitting the lunar surface. This is the earth shine, okay, which creates some noise in your measurements. If you are here, if you have a spacecraft here, the spacecraft can always observe the lunar far side. There is no earth shine because all of the bouncing of the sunlight will go to this portion of the moon, and you are kind of protected there. You can have continuous observations for 14 days, which is half of the period, and you can have a much better scientific product. And this is what we want to do with LUMIO. This is what we want to do with LUMIO, right? LUMIO will be in L2 and will monitor for 14 days per period the lunar far side and trying to detect meteoroid impacts. Now, let's see this chart and let's see why we want to do this. This chart is taken from this paper by Sykes et al. It reports, it's in a bilogarithmic scale, it reports on the x-axis, the kinetic energy of the impactor, and on the y-axis, the occurrence of impacts. How many impacts you have per year, okay? Now, the famous Chelyabinsk impacts, which occurred sometime in 2014, I guess, in Russia, it was at this energy. It was a huge one. It was not seen because it was coming, it was day, so you couldn't see it. And it was a huge impact, okay, but you have that one of these is very rare, okay? The dinosaur impact is probably around the bottom right corner of this, because these are also meteoroid and NEOs, right? And you have one every 100,000, if not millions here. The fireballs, those that you see at the Notre di San Lorenzo, for instance, you see them at these energies. The lunar impact flashes that you can observe, they occur between these energies. This is KT-TNT, is kiloton of TNT. 1 kiloton of TNT is the same energy as released by 1 ton of TNT. Okay, so it's quite a big bomb. Okay, so 10 to the minus 3 kiloton TNT is 1 ton of TNT. Okay, is this energy, right? So the lunar impact flashes are between, let's say, 10 to the minus 6 and 10 to the minus 1, those that we want to observe. We can see that we have no data here, and we have kind of uncertainty there. And this is what we want to do. We want to find new data here. Here we have no data because you have a limit from this side. These are ground-based survey with telescopes, and at some point you cannot resolve anymore because the rock becomes so tiny and cannot be seen. So the limit from this side is given by the resolution of the telescopes, and you have no data. The limit from this side, these are the ground-based measurement of lunar impact flashes. They are limited because you have not enough time, because you have only a few hours per night to observe. So we want to discover new points in this chart. We made a model, courtesy of Gianmario Merisio again, with modeling the meteor showers here, and we made a simulator called Megan, which can model the showers in a statistic way, and it can predict the number of impacts per year. Here you see solar longitude. When solar longitude is 0, it's 21st of March, and this is the year, right? And on the other y-axis, you have the cumulative number of impacts. When you tie this phenomenon with our payload and with our concept of operation, you can have the simulated number of impacts that you can detect. You can detect this every 14 days because in the other half of the period, you have this beta angle to be, when the beta angle is 0, you cannot, is less than 90, let's say, you cannot observe, so you don't see red stuff. You have to read the beta angle on the right y-axis and the number of detection on the left y-axis here, right? If we put all of this together, we can see that with a 1-year mission, we can have a lot of the red points here, and we can also have quite some points in the region where we have no data. Okay, there is a difference between, in the color code here, red, it means that you can measure the light and you can solve for the kinetic energy. Yellow, it means that you can only detect the occurrence of an impact, but it saturates your detector because it's too much light. You cannot measure the light, but you can only have a lower bound for the kinetic energy. This is the payload that we have designed in phase 0. This has been later on discussed with ESA, and we have another baseline now in which we have 2 detectors and a dichroic element in between to split the radiation. And the concept of operation is that you have to detect the impacts on board. How does it work? We look at the lunar far side and we take a number of frames per second. With LUMIO, we take 15 frames per second. Okay? So you have 1 frame, you have the previous one, you kind of subtract them. If from the subtraction you have only noise, you throw it away. If from the subtraction you can see a spike, there is something that is non-zero or greater than the noise level, it can be an impact. It can also be a galactic cosmic ray that hit your detector. That's why now we have 2 detectors to validate the measurement. But however, think of storing 15 frames per second and dumping these to the ground station. You will go in the terabytes after a couple of hours probably of taking pictures. So that's why in the statement of work that ESA issued, the requirement was that the operation had to be autonomous, right? And the CubeSat had to be independent from the mothership. Okay, so this is our concept of operation. This OBPDB stands from onboard payload data processing. We have a board, and our friends from S&T Norway are in charge of this task. For what concerns the orbit, we chose an L2 quasi-halo orbit, quasi-halo because it doesn't retrace, it's not periodic when you have the full system, the periodicity is lost. Because you have permanent full disk coverage in one picture, if your field of view is greater than 6 degrees, in one picture you have all of the full disk. We have permanent far-side observation. It's easily accessible from low lunar orbit. It's only a matter of 200 meters per second to go from low lunar orbit, elliptic low lunar orbit, to Sun Earth 2. It's free of eclipses, which is quite nice for the space mission. And moreover, it's a near 2-to-1 resonance. It means that the period of this orbit, it's about 14 days. The period, the synodic period of the moon around the Earth, when you take also in consideration the geometry of the sun, is a little bit greater than 28 days. It's 29 point something days. And it's exactly twice this orbit. It means that you can lock the operations and you can design your mission for one synodic period, and then you plug and play this period, and then you keep repeating it for all of the lifetime. Indeed, in the blue stuff, suppose the red square here is LUMIO. In the blue stuff, you have the scientific investigation that is done. In the orange portion of the orbit, you cannot do any science because the moon is illuminated as seen from LUMIO, right? So one can say that this is a wasted time. It's actually not wasted at all, because this is the nicest geometry to do autonomous navigation, because you have the moon that is always illuminated. So by using the same payload, without having the need of embarking another instrument, but by using the same payload here, you can take a picture of the moon, you can isolate the limb, this is called the limb, and the terminator line by manipulating the image, and you can fit, I'm not sure if you can see, there is a red circle fitting the moon. And if you know the radius of your red circle, and you know the radius of the moon because we know the radius of the moon, you can easily relate this with the range information. There is a simple arctangent in between, okay? Between the radius of your red circle and the distance that you are from the moon. You can have a scalar information, but however, if you knew the orientation of the spacecraft when you took the picture, you can have the vector to the moon. So you have a vector information. And you can feed these into an onboard filter, and you can solve for position and velocity. Okay, so we did the math courtesy of Vittorio Francese, and you could see that we have a dispersion before the maneuvers of less than 10 kilometer uncertainty in position, which is nice, and it enables autonomous navigation. This is called autonomous navigation. Standard navigation relies on contacting the ground station and measuring the range and range rate on the ground station. The spacecraft has been a little bit changed, but we have an onboard propulsion which was using this hybrid ADN system from VACO. We have a communication. Now, what I'm presenting is the outcome of the phase 0. These issues have been a little bit discussed with ESA. The ADCS is the attitude determination and control system, which has reaction wheels, star trackers, sun sensors, and IMU. And the power, you have 2 wings, and you have a ground space power distributor, and the power is courtesy of Kartik Mat, which is sitting there. This is the overview of how the spacecraft will look like, and this is the classic mass budget that you define in this very preliminary stage. You can see that the overall mass already margined is 21 kilograms of all of the system. We underwent the ESA assessment, and the general answer was that the mission is feasible. There were a number of points that were discussed and have been slightly modified and will be the focus of next phases of the design, namely the possibility of having direct communication of the Earth with the Earth, because the spacecraft is always visible from the ground station because it's free of eclipse and also free of occultations from the moon. We had a reassessment of the camera with having a 2 CCD and the radiation that is split onto CCDs. We had an increased thrust authority because we switched from that thruster to another one from Aerojet, but still keeping the overall delta V to less than 200 meters per second. And we merged two different computers, the attitude computer with the onboard payload data processing computer, by embarking a more powerful one. Strangely, for CubeSats, you have a lot of limitations with respect to standard satellites, but the computational power is not limited. This is because you embark components of the shelves that are used for terrestrial applications that most of times are not space qualified, okay? And because of that, you have actually more computing power than standard satellites. All of this to say that we did the mission. We were awarded the winner of the competition, and phase 0 was very successful because the concurrent design facility assessment said that the mission is feasible. It's a unique opportunity that we are much resolved to pursue it forward. We are almost there for next phases of the contract with ESA. We have to we will kick off in a few weeks, and at Polimi we want this to happen in the next 3 to 4 years. We are all set for the next mission phases. That's all I wanted to say. I wanted to share with you. I squeezed much information in a few minutes. We have reports that are 200 pages. But thank you for being here, and thanks for your attention.